stars start in stellar nebula, and then they go through a main sequence stage. They puff up into red giants, and those puffed up layers of gas are then expelled into a planetary nebula. In the center is a really hot core called a white dwarf, which emits a lot of powerful radiation that illuminates those outer layers of gas and makes these really beautiful images. Of planetary nebula.
Oh, I see why this was so big now.
This is my object, M57, the Ring Nebula. And I'm kind of biased because I think I chose this topic because they make very beautiful images. Specifically, my science goal was to find some sort of velocity pattern or gradient in the Ring Nebula, so I chose to place my slit of the spectrograph at 5 different positions on the nebula. I chose these positions. This is a very nice Hubble image of the Ring Nebula, by the way. 1 and 5 go directly through the rings. 2 and 4 go at the very, very edge of the rings, and position 3 goes just straight through the middle of the rings. And this is an estimation of where the slit is placed. It was mostly in the major axis, so I just made an estimate of where the slit was placed. These are the data that I took. They were taken on October 5th, 2019, with the Elliott 24-inch telescope's LIRIS 3 spectrograph with a spectral rating of 150. This table here, you can see, this is in chronological order. So the first row is the first set of frames taken, and the last row is the last set of frames taken. As you can see, all 5 positions were taken on October 5th, 2018. I actually took data on September 24th as well, but I didn't put down exactly where the slit was. So because my analysis required knowing exactly where it was, it ended up being kind of useless for my analysis, so I decided not to use that data. We're all observational astronomers, so we know that in order to do proper data analysis, we need to calibrate our frames. And so this is a comparison sort of thing. On the left is the raw uncalibrated frame, and on the right is the frame with bias and dark frame subtracted from it. As you can see here, within the 2 blue lines are the spectral lines you can see, and they're very much sharper in the bias and dark subtracted frame. Furthermore, from this, you will have to also subtract the background from it in order to get it fully calibrated, but I did that by taking a rectangle above the spectral lines and a rectangle below the spectral lines, taking the mean of that and subtracting it from the rectangle with the spectral lines. Additionally, in order to do spectral science, the frames that you're given with only have the position of the lines in terms of pixels, and you need the position in terms of wavelength. So in order to make that calibration, we took spectra of a neon calibration lamp, and that's useful because the lines in a neon calibration lamp, their wavelength positions are known. It's a laboratory determined thing. So you can plot something like this with the wavelength position of those neon calibration lamp lines with their pixel values, and you can get a relationship like this. And for my data, I got a pixel wavelength relationship of 0.87. So once you apply this pixel wavelength relationship, there we go, you should get a spectrum like this. And we're interested in these 2 features here. The feature on the right is a cluster of singly ionized nitrogen and hydrogen alpha lines, and the cluster on the left is the doubly ionized oxygen doublet. So we're going to be looking at all 3 of those species in this analysis. Let's look at them in more detail. So I took my data and I fit some Gaussian curves to them. And these are the doubly ionized oxygen lines. As you can see here, plotted are all of the positions. You can kind of see position 2 is plotted twice. This is because I took 2 different exposure times for position 2, but for the analysis, they were actually combined. So separate analysis was not conducted. They were combined in the analysis. And we can look at the other lines. So these are the singly ionized nitrogen lines. And the hydrogen alpha line. A thing I'd like to say is that if you compare the hydrogen alpha line with the first of the singly ionized nitrogen lines, they're very, very close together. The right of this plot here and the left of this plot here are very, very close. And so this was actually the determining factor in choosing the 150 grading. If those two lines were closer by maybe 5 to 10 angstroms even, we would not have been able to use the 150 grading because they probably would have started to mesh together. So it ended up working out nicely. So when we take velocity measurements, which is to say we compare the wavelength of the peaks with laboratory determined wavelengths, we can, well, I did that for each of the positions, and I found there was this interesting velocity gradient for hydrogen alpha and also for singly ionized nitrogen. But here we have hydrogen alpha, where the slowest velocities were in the center of the nebula, and the fastest velocities were on the outside, the edges of the nebula, in positions 1 and 5. So as you can see here, it kind of forms a gradient where it gets faster as it gets away from the center of the nebula. This is the same for singly ionized nitrogen. You can see, again, it's the slowest in the center, and it gets faster as you get further from the center. However, it does not show for doubly ionized oxygen. To kind of try and find an explanation for this gradient, I scoured the literature, and I found a paper that talked about the expansion rates of the gas of the nebula. And it said that the expansion rate of the gas at the center was slower than the expansion rate of the gas at the edges. However, this paper included not only radial velocity measurements, which spectral data provide, but also proper motion measurements. So because our data only had radial velocity measurements, we can't really say anything conclusive about the expansion rate of the gas in its entirety. So a future step might be to take some proper motion measurements in order to see if this matches the literature. Additionally, we took average velocities of each of the species across all 5 of the positions, and we did some statistical analysis, and we showed that all of these velocities were different from one another at the 99% confidence level. So you can see there's this sort of pattern that appears where the doubly ionized oxygen has a smaller velocity, a lesser velocity than the singly ionized nitrogen, which is less than the hydrogen alpha. And this pattern I also scoured the literature for, and I found that there was something called Wilson's law of homologous expansion in one of the papers, which basically states that ions of increasing ionization have less velocity, or slower velocities. And this exactly fits this pattern here. So in conclusion, the spectrum of M57 was studied, specifically the doubly ionized oxygen, the singly ionized nitrogen, and the hydrogen alpha species. A pattern of velocity was discovered between the 3 species where doubly ionized oxygen was less than singly ionized nitrogen, which is less than hydrogen alpha, and this is consistent with Wilson's law of homologous expansion in the literature. And a velocity gradient exists for hydrogen alpha and singly ionized nitrogen, but not for doubly ionized oxygen. This may be indicative of a gradient from the literature, but proper motions are required. Okay, it's not gonna turn, but thank you.
You could just do the arrow keys on there.
Yeah, I was just gonna say. The many thanks to the teaching staff of 1214 as well as Ani Chitti, and without them, this project would not have become a reality. Thank you. And I welcome any questions.